Hello and welcome to lecture 51 of the course Computational Complexity. In lecture 50, we started seeing the proof that permanent is Sharpie complete, right? So in fact, the permanent is Sharpie complete. The first part of the proof was that permanent is in Sharpie. In fact, what we showed was that 0, 1 permanent was in Sharpie, right? So 0, 1 permanent corresponded to counting the number of perfect matchings in a bipartite graph. And then we said that we will show that 0, 1 permanent is also Sharpie hard, in the sense that any function in Sharpie can be reduced to 0, 1 permanent, right? And this was a rather long proof, or is a rather long proof, and we said that we will follow 4 steps, and the first 2 steps we completed. We reduced sharp 3 side to sharp 3 side balanced, and then sharp 3 side balanced to -1, 0, 1 permanent. And what remains is to show that -1, 0, 1 permanent reduces to 0, 1 permanent. So this also follows, actually it's 2 steps. We will reduce -1, 0, 1 permanent to 0, 1 up to m permanent. So meaning it will be reduced to the problem of solving the permanent on a range of non-negative values, and then we will show that can be converted to a permanent of 0, 1 values. Okay, so both of these are rather short. So this particular lecture video also is going to be rather short, right? So we want to reduce. So the first part is to the third step, that is -1, 0, 1 permanent. How do we reduce to a non-negative bounded range permanent, right? So given a -1, 0, 1 matrix A, we will see how to get a 0, 1, 2 up to m matrix B. So m is some number that is depend on the dimensions of the permanent, dimensions of the matrix A, right? Such that the permanent of A can be obtained from the permanent of B. So it will not be the same, but you can get one from the other. So notice that a permanent is a summation of, right? So what was permanent? Permanent was right, this was nothing but summation over all permutations, product over all I equal to 1 to n, ai sigma I, right? And since we are dealing with matrices of -1, 0, 1, the products will be either 1, 0 or -1, right? And how many terms are there? So that there are n factorial permutations, or n factorial terms are there, and some of them could be 0, right? So the maximum this can be is that all of the terms turn out to be +1, so which is n factorial, and the smallest that this could be is that all the terms turn out to be -1, which is -n factorial, right? So permanent of a 0, 1 -1, 0, 1 matrix A is going to be bounded between -n factorial and +n factorial, right? So what we will do is to shift this to a completely positive domain, right? So what we will do is to, so right now we have this situation, right? The values could be anywhere from 0 to -n factorial to +n factorial, right? It could be anywhere in between. So what we will do is to shift this entire thing to the we will shift it that, maybe I'll use a different color, right? We will shift it so that the 0 goes to, so 0 to n factorial remain at the same place, but -n factorial and these values get shifted, right? So -n factorial will actually become 2 times n factorial, right? So using modular arithmetic, right? So it will be, so the point here is that the green values are all non-negative, right? Are all non-negative. So we will use modular arithmetic to move to this domain, right? So what we do is to set m to be twice n factorial plus 1, right? So in the mod m domain, everything is between starting from 0, 1, 2, 3 up to 2n factorial, right? So there is 2n plus 2n factorial plus 1 again becomes 0 mod m, right? So we look at each entry of A, the matrix A, and replace it with the equivalent mod m value of to get B, right? So 0 and 1, so A has three types of entries, 0, 1 and minus 1. So 0 and 1 just remain 0 and 1. However, minus 1 becomes m minus 1 in the modulo m setting, right? M minus 1 is actually 2n factorial, right? So now we compute the permanent of B where everything happens modulo m, right? Everything, so all multiplications, additions, everything happens in the modulo m world. So since everything happens in the modulo m, at the end we will get some number which could be anywhere from 0 to m minus 1, which is 0 to 2n factorial, right? So that's how we get this inequality. And if the value is anything between 0 and n factorial, right? If the, so in fact let me just say this, if the value is between 0 and n factorial, then it means that the permanent of A is, it is actually the permanent of A, right? Because that's how it is going to be, right? If it is 0 and n factorial, that's how we would have got there. However, if the permanent of B modulo m was greater than n factorial, meaning it is anywhere from n factorial plus 1 to 2n factorial, right? Or n to m minus 1, that means that it was actually in the negative range, and it was because we applied mod m, it came to the positive value. So this means that the permanent of A is, you take the permanent of B modulo m, whatever value that is, and you subtract m from there, right? Because it's, if for instance if it is if the permanent of B mod m, if this was, let's say, right, if this was, for instance, if this was right, suppose this was, let's say, 2m, or this will be something between 0 and 0 and n minus 1. Let's say suppose this is m minus 2, so then this corresponds to, this means that permanent of A is minus 2, right? If this is let's say just m plus 1, oh sorry, what I want to say is if this is n factorial plus 1, right, this means this minus m is 2n factorial plus 1, this will be minus n factorial, right? So like that, there is a correspondence between all the values of permanent B mod m and permanent A. So you just compute permanent B mod m, and you can compute permanent A using that, right? So that's how we reduce a permanent of a 0, 1, minus 1 matrix to a permanent of a matrix that has values in the range 0, 1, 2, 3 up to capital M. In fact, we have in fact the values will be up to m minus 1, and we are actually doing modulo m minus 1, right? So in fact this is, I could actually say this is true, but it's fine. 0, 1 to m is actually a superset of this. In fact, the matrix has only three values, 1, 0 and m minus 1, right? It's not even the entire range, but the permanent could be anywhere in these ranges, right? So that's how we complete this part. Minus 1, 0, 1 permanent reduces to 0, 1, 2 up to m permanent, where it's bounded positive values, right? So now what remains is the last part. If you are given a set of bounded positive values, a matrix that contain bounded positive values, how do we reduce this to a 0, 1 matrix such that the permanents are the same? So here the permanent needs a bit of computation, but we will here we will reduce the permanent of 0, 1 up to m matrix to another matrix C, right? such that the permanent of matrix C will be the same as permanent of matrix A. In fact, this is slightly easier to view it in the graph setting. So we said that the permanent corresponds to the sum of the weighted cycle covers, sum of the weights of the weighted cycle covers, right? So sum of all the cycle covers, all the weighted cycle covers, where the weight of a cycle cover is just the product of all the weights, right? So let us see what this means. So what we will do is we will see how each the graph. So the permanent of the, let's say a matrix with 0 1 up to m values corresponds to a matrix or corresponds to a graph that has edge weights 0 1 2 3 up to capital M. Now we will see how each of these values that are not 0 and 1 can be replaced by some gadgets or some equivalent graphs. The parts can be replaced by equivalent graphs which have only 0 and weights, but we get the same, the cycle covers will, the weight of the cycle covers will be unchanged. Okay, let's see why or how. So first let us see, suppose there is a edge of weight 2 power m, right? So it need not, any edge need not be of this weight, it could be, it need not be of, need not have its weight as power of 2, but let's, as a first step, let's see an edge of weight 2 power m. So now we can replace that edge with this kind of network. So this may look familiar to you. In fact, we use the same kind of, we use the same gadget in the proof where we saw that if we are able to count the number of cycles in a graph in polynomial time, then we can decide whether there exists a Hamiltonian cycle, right? So we use the same idea. So the point is that now the graph on the right hand side, the network on the right hand side has the same, starts with U, ends with V, but look at the number of ways in which you can reach V from U. So you can see that at each there are m stages, m intermediate stages, and each stage you have two options to choose, either remain on the top or go to the bottom, right? So there are 2 power m paths in this network from U to V. So if you replace this edge uv of weight 2 power m with this network, what happens is that any cycle that originally went through uv in the graph on the left hand side, now there are any cycle that went through uv, now there are, this edge uv is replaced by 2 power m possible paths from u to v, and these edges, these vertices, intermediate vertices, don't interact with anything else outside in the graph. So the edge uv is replaced by 2 power m possible paths, right? So edge uv is replaced by two power m u to v paths. So instead of there being one cycle for which uv contributes 2 power m, now we have 2 power m different cycles, each of which for which the uv path contributes 1. So that's how we get an equivalent representation. And here in the graph on the right hand side, all the edges have weight 1, right? And including many edges that have weight 0, right? So for instance, this edge, there is no such edge, but this is like an edge of weight 0. Okay, so now we have told how to, we have seen how to convert a edge with weight 2 power m or a power of 2 to a network, to a 0 1, a network with 0 1 weights. So now what if it is not a power of 2? So let us see, it is a sum of 2 powers of 2. Let's say there is an edge with weight 2 power m1 plus 2 power m2. Well, what we can do is to replace, okay, before getting there, then we may need to do one more thing, because a cycle cover may not actually cover all these vertices from U to V, right? Because let's say a cycle, a cycle cover that takes this path it does not really use the bottom edges. So what we'll also need to do is to actually put self loops all over here, right, and also in the top, so that the edges that are not used can just participate in the cycle. The vertices that are not used in the cycle cover can participate using these self loops. Okay, so now let's come back to this. What if an edge has a weight that is not a power of 2, right? So let's say 2 power m1 plus 2 power m2. Well, what we can do is just to have see it as two parallel edges, right? And where each, like 2 power m1 edge of weight 2 power m1 and edge of weight 2 power m2, and then what we can do is to replace each of these edges with the corresponding network that we saw. So one network which has m layers, and one network that has m1 layers, and one network that has m2 layers, right? And any number, as we all know, can be represented as a sum of powers of 2. So any positive, any non-negative weight can be represented as sum of powers of 2, and consequently as a bunch of networks like this. So that will, if there is an edge of weight w from u to v, then what we will do is to replace it with a network of edges, 0 1 weight edges from u to v, so that instead of there being an edge and one edge of weight w, now in the network there will be w possible cycle covers that take this path from u to v, right? So this is how you will, of course I'm just talking in the graph setting, but all of this has a corresponding situation or corresponding equivalent in the matrix situation as well. So this is how we can replace a matrix B which has 0 1 2 up to m values to a 0 1 matrix, right? So here both 2 power m1 and 2 power m2 will be replaced by 0 1, a network that has only 0 1 weight edges, and that completes the proof. So that is the last part that we had left. That completes the proof that 0 1 permanent is Sharpie complete. Right? So even permanent, even restricted to 0 1 values, is Sharpie complete. Right. So this is Welian's theorem from 1979, that even permanent. So permanent, one may think that permanent is not such a difficult problem, because permanent is just corresponds to the counting of the number of matchings in a bipartite graph, right? So the decision version of the problem is easy, just like we said about the number of counting the number of cycles. However, we see here that the counting version of the problem, right, counting the number of perfect matches in a bipartite graph, this is Sharpie complete, meaning you take any problem in Sharpie, then you can reduce to permanent. So yeah, with that I conclude this lecture, and yeah, thank you.